interruptions. For our Zoom audience, in case of any inconvenience that may arise during the session, we ask that you send a direct message to the staff who have the name Implexis staff in this session. If you would like to ask Dr. Yakovenko a question, please send it as a direct message to Implexis Q&A. For those of you who are attending in person at the Congress Center, you can send your questions to him through our staff. Today, we are joined by Victor Yakovenko. Dr. Victor Yakovenko is a professor of physics at the University of Maryland. He's a fellow of the American Physical Society and was a recipient of the prestigious David and Lucille Packard Fellowship in Science and Engineering at the Alfred P. Sloan Research Fellowship. He's a theoretical physicist with more than 35 years of research experience in studying electronic properties of various materials. In addition, he joined the emergent econophysics movement around the year 2000 by publishing his first econophysics paper. Over the next 20 years, his ideas became increasingly popular and initiated an expanding wave of follow-up papers by many researchers around the world. The work of Yakovenko has also been covered in popular social media, such as the New York Times Magazine, American Scientist, The New Scientist, Australian Financial Review, Science Magazine, and the UK Engineering and Technology Magazine. Yakovenko has given about 150 invited talks on this subject. He received his master's in physics and engineering from the Moscow Physical Technical Institute in 1984, and his PhD in theoretical physics from the Landau Institute for Theoretical Physics, Moscow in 1987, where he was also employed as research scientist. In 1991, he began a postdoc at the Department of Physics, Rutgers University. In 1993, he joined the University of Maryland, College Park as assistant professor and became an associate professor in 1999 and full professor in 2004. Welcome, Dr. Yakovenko.
Okay, thank you very much for the opportunity to give this talk. Let me share my screen first, right? Share screen. Okay. So my screen is shared now. Let me, okay. And let me make sure that I have annotations enabled. Okay, so just a second. Okay, let's see if it works now. Yes, now it works, I think. Okay. Okay, great. So let us start. So first of all, yeah, I would like to mention a couple of things that it's my actually second time I'm giving this presentation and Monterey Institute of Technology. The first time was actually in 2004. That's actually when I gave an earlier version of this talk in Monterey. That was in person at that time, but now it is in virtual online. So basically, the talk today would be an overview of the. I mean, I have been working on this subject for quite a long time. My first paper was published in the year 2000. The title of this paper was Statistical Mechanics of Money, and that will be the first part of my talk. Just to introduce the ideas, the basic ideas. And since then, there was many follow-up publications. By the way, this paper of 2000, it is now my most cited paper. It is, exceeded any citation that I had on condensed matter, quantum condensed matter physics, which is my original field anyway. So anyway, so there were many papers. I will not cover. I mean, I will. Okay, so let's see. Just a sec. Just a second. What's going on? Just a second. So what's going on? Clear. Okay, fine. So I will not cover. I mean, I will kind of do a quick overview of these many subjects since that time, and my most recent paper was actually published in 2022 this year in British Journal of Philosophical Transaction of Royal Society. Okay, so it will be a quick overview of this. So if I will start with the first topic of statistical mechanics of money. Then I will, if there is time, maybe I will discuss that, if there is time, but I will spend also much time on this. Next subject is showing actual data on two-class income distribution, and then hopefully discuss inequality in energy consumption. Yeah, maybe since I'm on the first slide, I also mentioned I'm originally from Ukraine, and that's I'm supporting the country. Okay, so anyway, so let me start with the first subject and to introduce this main idea. Okay, so I will start with a kind of little bit of historical note. So I'll show you two portraits. So this is Ludwig Boltzmann, one of the founders of statistical physics. This is, of course, very well-known name to physicists. And one of the things that is associated, that's what we teach in courses of statistical physics. And what is associated with his name, among other things, is a so-called Boltzmann-Gibbs probability distribution, which basically tells us, for those of you who study statistical physics or thermodynamics, it says that probability distribution of energy is given by exponential, more precisely, exponential decrease in function of energy. So it's given by this formula, where epsilon is energy and T is temperature. Okay, so that's called Boltzmann-Gibbs distribution in statistical physics. I will not go into too much detail because this is standard textbook stuff in principle. But now I'll show another portrait. This is Vilfredo Pareto, who lived about the same time, and to some degree looked a little bit similar. He is Italian. He originally was educated as an engineer in Politecnico di Torino in Italy. So he's an engineer by education, but physicist, if you like. But then he started doing economics. He became actually a very well-known economist, and there are various things unknown. This name is very well known to the economists. And one of the things that's associated with his name is power law. So in those days, he actually looked at probability distribution of income and wealth using the data available at the time, late 19th century, and he concluded that it is distributed by a power law function. So bottom line is, for the purpose of this talk, these two, simplest mathematical functions, exponential function and power law function, I will associate one of them with the name of Boltzmann, another one with the name of Pareto. They will recurrently appear in the talk, as you will see. So I wanted to start with this brief historical introduction, and and you will hear these names again as we proceed through the talk. Okay, so on the next slide, I will show you some sort of analogy between distributions of energy and money or income that originally started this whole subject. Okay, so let me start with this analogy. Okay, so this is one of the simplest ideas. Okay, first we consider an ensemble of atoms. So, say like gas in this room, gas in the air, air in this room. Okay. And then atoms with like ideal gas. So atoms move around, right? And they experience collisions. So let's consider this collision between two atoms or molecules, okay? Like oxygen molecules, whatever. So you have one molecule with energy epsilon 1, another molecule with energy epsilon 2. So they collide, okay? And then they fly away. So, but in the process of collision, some energy delta epsilon get transferred. So some energy is transferred from one atom to another. So let's say this molecule flies away with a little bit higher energy, and this of course with lower energy because there is conservation of energy in the collision. So this is very familiar. It's like a collision of billiard balls, balls in mechanics. So energy gets transferred in the process of collisions. Okay, that's mechanics. But now if you have a very big ensemble of these objects, there is a huge number of molecules, in the room, right? They continue collide and collide. So we deal with a statistical ensemble. So now we deal with statistical mechanics as opposed to simple mechanics. And if you have a big ensemble of those atoms, well, if you keep this box, let's say closed system, isolated box, okay, after some time, it will come to something called statistical equilibrium. So it will develop some sort of probability distribution of energy. So in other words, if you measure randomly, energies of those molecules, you will get different values, but you will get some sort of probability distribution of those energies. And there is an interesting question: what is this equilibrium probability distribution of energies? What is the probability distribution of energies in this gas in statistical equilibrium, in thermal equilibrium, okay? And this is very standard question discussed in pretty much all textbooks, of statistical physics. There are many ways to derive it. So I'll go briefly one way, but there are other ways to derive it. One way to derive it from something called detail balance. So in other words, you may consider this configuration. You may ask the rate of transitions from this configuration, epsilon 1, epsilon 2, to the final configuration. And the number of those transitions, the rate of those transitions, is a product of the following. First of all, it involves the probability of making transition from, say, this configuration to that configuration. And you can calculate it either using classical mechanics or quantum mechanics, whatever. But then you multiply by occupation numbers, how many atoms are in this state and how many atoms in that state. So you multiply by occupation number of the initial states, state 1 and state 2. So the product of three factors give you the rate of transition from this configuration to that configuration, right? Agree with that? Okay. But on the other hand, reverse transitions are also possible. You may consider reverse processes when transition takes place from this configuration to that configuration. In other words, you may consider this configuration as initial, then there is collision in reverse, and then this will be the final configuration. Okay, that will be proportional of probability of making reverse transition multiplied by occupation numbers of this state and that state, this and this state, okay? So now, in equilibrium, in statistical equilibrium, when system reaches, when the probability distribution becomes stationary and time independent, right? So the number of transitions in this direction and in this direction must be equal, so that on average nothing actually changes. System is stationary. So this is called principle of detail balance. So we say this rate must be equal to this rate in statistical equilibrium. Okay, so far so good. And now something very interesting. Fundamental laws of physics, they have time reversal symmetry. So that means the probability of making transition in one direction and in the opposite direction, they're actually exactly equal. In other words, you can play movie forward or can play movie backward, and both are compatible with laws of physics. So for that reason, we can cancel out those probabilities of transition. And after that, we arrive to two very simple equations. And this equation says that energy is additive, whereas probability is multiplicative. So in other words, the product of probability is equal to this product of probabilities. Now, these two equations, this and this, they have very simple solution, and this is exponential. It's a solution of this equation is exponential function. So that's kind of end of derivation. it's amazingly kind of amazingly simple. So see, if probability is exponential function of energy, then of course, if this equation is satisfied, then second equation is also satisfied automatically. This is a property of exponential function. Okay, now because energy is a dimensional variable, we need to divide by some constant because the argument must be dimensionless. We need to divide by some constant, which is called temperature, something like average energy, which is basically the average energy of the system. So notice that this distribution is kind of universal in equilibrium. It does not depend on details of the model. And of course, if there is certain symmetry satisfied. So anyway, this is one derivation of, and this is called Boltzmann-Gibbs distribution, the exponential one, okay? Now, there are other derivations. You can find actually several in textbooks. Another one is maximization of entropy. So you define entropy of the system. Okay, maybe I'll discuss it later. But anyway, so you can obtain the same distribution by maximizing entropy of the distribution under the constraint that total energy system is fixed. If you have an isolated system, total energy is fixed. And as Boltzmann have shown, if you maximize entropy subject to this constraint, you also get exponential distribution. So that's pretty much all I wanted to say about statistical physics. This is a summary. Well, you presumably take the whole semester course on statistical physics and thermodynamics, but this is a very brief summary. And now I'm going to switch to, well, economics. Okay. So now I will introduce this analogy. And I often say that in this whole field, I made only two contributions. Okay, so one I will show you now, and second I will show you later. My first contribution is to this field. I replaced the label. Okay, watch this. Okay, you see this energy, right? And now I say money. Okay, so that's it. I replace the label. So what does it mean? Now I consider a economic transaction between a transaction between economic agents. Okay, so now I have an ensemble of not atoms, not molecules, but an ensemble of people, participants of the economy. Let's say people in this room or something like this. So we have now the economy is a big statistical ensemble, right? Because there are millions of people interacting, etc. So it is a statistical ensemble of some sort, okay? And when people engage in economic transactions, right, I will consider specifically what is called monetary economics, okay? So like whether we like it or not, when we make economic transactions, right, we pay money, right? So let's consider economic transaction between these two agents. So this is one agent and has money balance M1. This is like bank account of something. This agent has an account and the money balance of this agent M1. And then there is another agent who has money balance M2, okay? And then there is a transaction. So let's say agent number 2 buys some product from agent number 1, okay? So let's say I usually have a name in the room, but I ask, okay, so suppose I buy say a bottle of water from somebody in the room, okay? So I'm the agent number 2. So basically I give you, somebody in the room, I give you, say, $1 or something, okay? And you give me a bottle of water, okay? So this is our transaction, the purchase, right? Then I drink water, water disappears, and I never see you again, you never see me again, okay? But what is the net result? You see, your money balance is $1 up, and my money balance is $1 down, right? So in these economic transactions, money get transferred from one account to another account. And that's pretty much how all economic transactions work. This is kind of the law of accounting. That money get transferred from one account to another account, right? Would you agree with that? Okay, I think pretty much everybody familiar with this, especially this is done on computers usually, digital transactions. But anyway, as you can see, the sum of initial and final money balances of these two agents are the same because money is only transferred from one agent to another, right? So there is, looks like there is a local conservation law of money in this transaction, right? And now there is a question. Suppose you have now a big ensemble and many people engage in many transactions, etc. System is big, kind of random, whatever. And the question, and let's say it is isolated to make it idealization. So the question is, what is the equilibrium probability distribution of money in this system? That's a good question to ask, right? And so basically my conjecture was that by analogy with statistical physics, I would guess that probability distribution of money in this ensemble of economic agents would be given by, well, similar exponential distribution of it will be given by exponential function of money. So it will be exponential decreasing function of money. And because money again has some dimensions like dollars or whatever, we need to put some parameter scale, which I call money temperature, which is simply the average amount of money per agent, basically. Okay. So that's basically the main idea for the analogy. Now, let me show you a computer animation to illustrate this idea better. Okay, so this is a kind of very simple-minded computer animation of the following kind. We start with a big number of agents, okay, with a big number of agents here. And initially, we give everybody the same money balance. So let's say 10 units, $10 or something, okay? So now initial distribution is a delta function, right? So delta function basically means that we prepare the system in a state of perfect equality. So everybody has exactly the same money balance. So everybody is equal in that sense, a state of perfect equality, right? That's initial state, we prepare this on computer. And then we start making transactions. I will start in a moment. So I will start simulation and animation. And, basically it works like this. The algorithm is the following. I pick a pair of agents randomly, and every transaction for simplicity would be $1, okay? So I transfer $1 from one agent to another. And then I pick another pair of agents, another $1, and so on. So I pick pairs of agents, and in each transaction, I transfer $1. So let's see what happens to the distribution, okay? So as you see, the distribution starts broadening, okay? So now it was delta function, right? Now it's not delta function, it has kind of Gaussian shape. Okay, and it has now non-zero widths, okay? So widths means the following, that, first of all, it's a closed system. It's a closed system, so the total amount of money in the system is conserved by construction. So that means the center of mass, the first moment, remains constant. But the second moment, the width of the distribution, or rather I should draw it maybe like this, it starts expanding, so it's broadening. So which basically means that by pure randomness, some of the agents end up with higher money balance, and some of the agents end up with lower money balance. So what we see is that some sort of inequality spontaneously develops in the system. So agents now cannot have different money balances. Okay, this inequality spontaneously develops in the system. So from physics point of view, this is basically diffusion, right? If you drop a piece of sugar, say in a tea, a cup of tea, then the sugar molecules start to spread around. They will not stay in the same place, they will spread around. So this process is basically diffusion in money space, okay? But I stopped the animation. Let's see what happens further if I continue animation. If I continue animation, the distribution continued to broaden, but now what you see is that it becomes asymmetric. So why it is asymmetric? Because I put a boundary condition at 0, which I did not mention initially. I actually put a boundary condition at 0, which means the following, that I do not allow money balance below 0. So if somebody spent all the money, okay, let's say if I spent all my money, my balance is 0, okay, then I cannot buy anything, right? I cannot buy anything because I don't have any money, right? So, and so how it is implemented in this simulation, it is like this, that if you pick an agent for transaction and this agent has no money to pay, we simply skip transaction, go to next agent. Okay, so in this way, but we do not allow balance to go below 0. So in that sense, the 0 balance is like what we call in physics ground state. In physics, it's like state of the lowest possible energy. So for example, in a gas, energy is kinetic energy, so it is positive. So 0 energy, it means atoms are not moving. That is the lowest possible energy. And the existence of ground state is very important, in fact, essential for stability, for statistical stability of physical systems. So here the 0 balance also plays the role of ground state. And so as the probability distribution broadens in both directions, it can broaden unlimitedly to the positive direction because there is no limit. We don't impose any limit. But it starts to pile up and accumulate near 0 because it cannot go beyond this boundary. So that's why it becomes asymmetric. It starts to accumulate around 0 because of the boundary condition. So if you continue running simulation and wait long enough, eventually this distribution arrives to this exponential shape. So the red curve here is simply a graph of exponential function. And that is the Boltzmann-Gibbs distribution that I mentioned earlier. And so basically the distribution eventually approaches and saturates at this exponential distribution. And then it doesn't change anymore. So simulation continues, agents continue changing money change hands, etc. But this distribution function becomes stationary. So this is what we call in physics statistical equilibrium, when probability distribution does not change, even though the individual, participants continue to, individual dynamics continues, okay? Okay, so that is an illustration, kind of dynamical illustration of how this equilibrium Boltzmann-Gibbs distribution develops. And by the way, these days when I teach statistical physics, I actually use this animation for illustration because in a way, it's easier to explain with money than with energy. Okay, so as I said, it's just changing label. If I put energy, that would be physics. If I say money, it becomes economics. Okay. So that's basically what we obtain. And what is shown at the bottom line, is this entropy as a function of time. So you see the initial distribution, the delta function distribution, actually had 0 entropy. Okay. So again, now I maybe briefly remind you, if you study statistical physics, what is entropy? Entropy is a logarithm of multiplicity. Okay, so what is multiplicity? It's the number of microscopic ways to produce the same kind of macroscopic configuration. To be more specific, it's a number of microscopic ways to produce different microscopic ways to produce a given histogram. So for example, for initial distribution was a delta function. Everybody had, every agent had balance of $10, right? There is only one way to make it, there's only one possible configuration like that. Okay, so everybody has $10, that is it. So multiplicity is 1 because there's only one configuration. Logarithm of 1 is 0. So the entropy of the initial configuration was 0. And then what happens is the second law of thermodynamics says that the entropy of a physical system spontaneously increases in time. So starting from 0 entropy, okay, it then spontaneously increases to the maximal possible value and then saturates. And as Boltzmann have proved mathematically, this exponential distribution, in fact, is the one that maximizes entropy. Okay, because you may see that, for example, the multiplicity is actually pretty high because, for example, my money balance may be $10 and somebody else is in the room, their balance is $20. That's one microscopic configuration, right? But it could be the other way around, right? It may be that I have $20 and somebody in the room has $10. Okay, so that is different microscopic configuration, right? Because we are different people, so we have different names. But it doesn't change the histogram. The histogram is the same. And so one can calculate combinatorially. It's pretty simple mathematical calculation. Combinatorially, in how many ways one can produce the same histogram by doing all kind of permutations of the people, of the agents, and then show that, in fact, exponential distribution actually maximizes multiplicity. That means maximizes entropy, okay? So then basically now what is conclusion of this? This is now coming to conclusion of the first part of my talk. Okay, what's the conclusion? My conclusion is the following. There are several conclusions. First statement, the state of perfect equality, the delta function, is totally unstable. You can artificially prepare a system in this initial state, but the moment you start doing any transaction, some sort of inequality spontaneously develops in the system, okay? So equality is totally unstable, whereas inequality is very stable. Okay, and now this first statement. Second statement, I would call this exponential distribution from physics point of view, I would call it the natural inequality. Natural meaning that it is the distribution that maximizes entropy, okay? And also, you see, this is a very simple model. The model is a toy model, is intentionally done very, very, very simplistic. First of all, this is a model, I would say, it's an equal opportunity model, because all agents are treated equally from statistical points of view. So in other words, every agent has equal probability to picked up for any transaction. So there is no bias, discrimination, preferences, individual attributes like skills, education, whatever. Okay, so in other words, it's a pure this unequal distribution originates not because agents have different inner qualities, but because it is a statistical ensemble, right? So for example, oxygen molecules, they're exactly the same. They do not have any, individual differences. And yet the energies of oxygen molecules in a gas are vastly different. There are few oxygen molecules with high energy and many oxygen molecules with low energy, which also sounds like society, very few rich people and very many, poor people. Okay, yes, and also I should say this is a model, if you like, highly stylized model of a free market. Free market in the sense that any agent can interact with any other agent, statistically, again. There's no structure, no regulations, no institution. Again, it's a very, very stylized model of, if you like free market. I mean, in some, extreme sense, if you like. It's not due, in other words, this inequality is not due to the structure of the system, but actually due to complete absence of the structure in the system, which is of course not realistic. Real societies do have structure and real people do have differences. But once you introduce those, they may, they can modify this curve in further. So in other words, this curve, I would say, would be, from my point of view, this would be like a reference point. That is some sort of inequality shape that we would have expected. If you have purely statistical ensemble, no other structure, it may or may not correspond to reality because reality is a lot more complicated. But that's like a starting point, like a baseline for comparison. At this point, I would like to actually stop a little bit and invite questions. That was the first part of my talk. So if anybody has any, kind of quick questions before we move on. Anybody would like to ask some questions or clarifications or something? Okay, fine. So let me then, if no people will immediately come with questions. Okay, so let me move on. So the second part of my talk would be about debt, but this is a little bit of deviation. So let me maybe skip it for now. And if somebody asks that question later, maybe at the end of the talk, maybe I'll go to debt. But for this moment, let me move to empirical data, because that's also very important. Now, this was purely theoretical computer simulation. I mean, it's a computer simulation of a very primitive model. And so it may have nothing to do with reality. I mean, it can be just, toy model. So basically what we wanted to do next is actually compare with the data. Okay, and then for the next like 20 or so years, we are looking at all kind of various kinds of data to see what happens in real economics. Okay, so let me now proceed. Okay, so let me skip this slide about that. I may come back to it if you ask me questions at the end. Let me now go to the third part of my talk, which is about empirical data on income distribution, okay? So what happened is the following, that of course my original presentation, I must warn you that there is a little bit of logical disconnect between the first part of my talk, which is just finished, and my second part, which I'm starting now. In the second part about empirical data, right? And the problem is the following, that originally we wanted to find data on money distribution, right? Because my prediction or expectation was that probability distribution of money would be exponential, and I would like to compare with the data. But it turns out very difficult to find data on money balances, okay? Some big banks, may have this data, etc. But this data is very difficult to get. I didn't manage to get this data. On the other hand, there is a lot of data on income distribution, okay? Now, income is not the same as money. Income is more like flux of money, because income is like annual income, like how much money you receive, say, per year. Like my annual income is some number, right? This is more, by physics analogy, this is more like power as opposed to energy, because this is money per unit time. This is influx. By income, by definition, is influx of money, how much money you receive per unit time. Of course, you also spend money. Money goes out. That's called expenditures. Okay, so these are two fluxes: money flow in and money flow out. So that's different from money itself, which is like a balance, how much balance you have. That is not the same. But conceptually it is not the same. But the point is that data on income distribution is quite widely available, because this is collected by all kinds of government organizations. You'll see there's a lot of data available easily, freely. So we decided to look at income inequality, just empirically, okay? Even though it's not the same as money inequality. So because there is data. So what we did first, we went to, this was done like, early 2000s. We went to different websites where there is data. So we went to Bureau of Census, United States Bureau of Census, which surveys population, and it is available. We can download it, raw data. This was for 96 because we did it, then, but I will show you more recent data. We downloaded raw data. Of course, it is a sample. So the census is a sample of population. It's not the whole population, some like 10,000 records or something. And then I made a histogram. So on this graph, what is shown is, individual income in thousands of dollars. So this is kilo dollars. This is $120,000. Okay. And what we did, we divided this axis into some kind of bins and counted how many people have income in different bins. So in other words, we made the histogram. So we constructed histogram ourselves from the raw data. Okay, and this is the histogram. Okay, so the histogram, yeah, that's the histogram that we constructed. Okay, and the solid, this is empirical data, and solid line, it's a fit to exponential function, right? Because I already motivated in the previous part. This was motivation that, well, we are interested. Would it agree with exponential? And you see, it actually does agree with exponential quite well. You see here, there's a pretty good agreement. Right here, there is discrepancy, but this is at the very, very low end, because this is below $5,000 per year, which is a very low income. So this is really near the boundary conditions, And so one would expect some kind of deviations near the boundary, but otherwise it's a pretty good agreement. Now, to see this agreement even better, that's something we learn in physics when we make visualization of the data. To see the agreement really well, it is the following, it is the best idea is to change coordinates in such a way that this relation becomes a straight line. So if you have exponential function, it is a base to take logarithm. So if you take logarithm of exponential function, right, it becomes linear function, right? So in other words, we should make this graph. You see, this graph is done where scale is linear. We have linear scale for income, and we have linear scale for probability, right? But it's better to do it what's called log linear graph. So now this is in the inset. So income is in linear scale, but probability is in logarithmic scale. So in other words, here we plot logarithm of probability as a function of income, and then data fall in a straight line. So now it's a logarithm of this function, so it's a straight line. So this graph is exactly the same as this one. It's just plotted in log linear scale. Okay, and you see the agreement is really great. Okay, again, this deviation at the end looks much smaller in logarithmic scale because that is a natural scale. Okay, so we saw that, well, we found that, in fact, income distribution, does follow exponential law. And that was totally unknown to the economists. So we basically discovered, if nothing else, a new empirical relation, which was not known to economists, not known to statisticians. So even though they had all available data, data is public, anybody can go and download this data, but nobody did. In other words, let's put it this way. This is my second contribution. So my second contribution to this field is, as a physicist, I made a graph of publicly available data. You see, that's it, right? Okay. Physicists know how to do this, but those people do not. Okay. Now, of course, it takes some thinking how to make this graph. You need to use log linear scale and all that. You know, you need some little bit, it's a little bit of art. But anyway, we made this graph. We discovered exponential law, and nobody knew about it. If you ask random economists, what is actually the distribution, they would probably tell you something like log normal or something else, but in fact it is exponential. And so we published second paper. The first paper was published in 2000, that was Statistical Mechanics of Money. Second paper 2001 called Evidence for Exponential Distribution of Income. Okay, however, this income here is limited by some, this data set does not cover very high income, so it's limited by some, by something. Okay. And what about very high income? And it turns out that at very high income, the law actually changes. It becomes something different. And so, but for that, we need different data source, because census, this is survey of population, a sample of population. They simply do not cover very high income. This is outside of the ensemble. So we need another data source. And for another data source, we went to the American Tax Agent, Internal Revenue Service, which is the American tax agency. Okay. And again, all this data is publicly available. So this aggregated statistical data, okay, publicly available. So we download the data from their website. And this is much bigger data set because, in principle, everybody is supposed to report their income for the tax purposes. So this is like 100 million, tax reports every year. Okay, it's a huge data set. And so we downloaded again raw data from IRS. There is some small remark here that the data, the way it is published, they publish this data at a certain income levels. Okay, for example, here it is $1 million, $500,000, 300,000, etc. So now we cannot make histogram because the levels of reporting are there, they're decided by IRS. We don't have control over it. So for this purpose, it's more practical to plot what's called cumulative distribution. Cumulative distribution is an integral of probability density. I'm not sure if I have definitions, but there is probability density, and the integral of probability density is called cumulative distribution. But the good news is that if you take exponential distribution, the integral is still exponential. The integral of exponential function is exponential function. And if you take power law function, the integral of power law function is also power law function. So the laws are, remain more or less the same. So anyway, so the inset here shows the data in log linear scale. Again, so this is per horizontal axis. This is what they call adjusted gross income in $1,000. So this is $100,000 in linear scale. But the vertical axis is a cumulative probability distribution in logarithmic scale. And again, you see the data fall on a straight line. Okay. So again, we see that the lower part of the distribution follows exponential law, which I call Boltzmann-Gibbs distribution. Okay. But what about high end, very high income? For very high income, it is more practical to use log scale. So now this income is also plotted in logarithmic scale. So this is a logarithm of income, right? So this is log scale. Income is logarithmic and cumulative probability is logarithmic. And so the exponential law is not a straight line anymore. It goes like this. But what you notice is that the upper part of the distribution becomes a straight line. A straight line in log coordinates means power law. And as you remember the first slide, I associate the power law with Pareto, with the name of Pareto. So bottom line, what you see is that the whole distribution can be very well fitted by two simplest mathematical functions, which I showed at the first slide, which is exponential function at the lower end and power law function at the high end. And well, there is some crossover point between these two fits. And so this is like, I see like the evidence for a two-class society. So in other words, we have, so basically this is the lower class and this is upper class. And this is boundary between them. You can take intersection point of these two fits as a boundary between two classes. And then you can read off parameters of these classes. For example, how many people are in the upper class, right? So you take intersection point, go here, right? And this is 1, 2, 3%, or this is 10%, right? So about 3%. So bottom line, see that the number of people, the fraction of population in the upper class, which follows power law, is about 3% of population. Okay, whereas the lower class exponential is the remaining 97% of population. So bottom line is we see that the great majority of population belongs to the lower class, and a very small fraction, few percent, the number changes over time. It's now about 5% or so, maybe 6%, but it's still a very small number, is in upper class. Okay, so we see evidence for well, we call two-class structure, two-class society, and this is purely empirical data analysis. It's not driven by some social, theories or whatever. It's just it's like data science. You just make a graph of available data, and you see what you see on the data graph. So this is just data science, if you like. Okay. Yes, and another thing which I wanted to point out that there is no such thing as middle class. Okay, because if you read like newspapers or something, they often say middle class. And from my perspective, from the data science perspective, there is no such thing as middle class. There is only lower class, which is exponential, and upper class, which is power law, and that is it. Okay. If anybody claims that there is middle class somewhere, tell me. So this curve is completely smooth, completely from $100,000 per year to zero. Okay, it's completely smooth in our straight line. So if anybody wants to put a boundary for middle class, okay, let's say this will be middle class, this will be lower class, tell me, where to put it. I don't see any structure. Okay. So, and by the way, there is no commonly accepted definition of middle class in economic literature. Okay, so anybody who writes, any articles about middle class, they make up their own definition of middle class. There's no consistency whatsoever. And so, in my opinion, there's no such thing as middle class. Okay, there are only two classes. Okay, great. So this is just one year, one particular year. This was 97 because we analyzed data about the sun. That's pretty old data, really old data. What about more recent years? And then we analyzed data for more recent years for the next 35 or so years of data, and basically found the same structure. I will show you in the next slide. But one thing I need to tell you is some rescaling. Remember that this exponential distribution, right? It has a parameter which I call income temperature, which is simply the average income, the scale. And of course, because of inflation, average income changes in time. In fact, it increased by factor 2.5 in like 30 years, in nominal dollars. So basically, the income temperature basically increases, well, mostly in nominal dollars. So basically, its scale changes. So what we need to do, we need to rescale. We need to normalize income to the average income in this year. And the way we do is we do this analysis for every year, and this parameter temperature, this can be obtained simply as a slope of this curve, right? It's the inverse slope of this curve, okay? So what we did basically is that for every year, we made this graph, a log linear scale. We get a straight line, we determine slope of this line. From slope, we determine income temperature, that means the average income, and then we normalize to this average income. And that I will show in the next graph. Oh, I forget to say this distribution, actually known also in physics, two-class distribution. The lower part is called thermal, this one, and upper class is called superthermal, that is power law. And this is actually very well known in things like plasma physics, astrophysics, cosmic rays, and so on. I mean, there are statistical systems in physics that exhibit similar behavior. Okay, so it's not only like social. It's actually in space science, plasma physics. This is actually quite well known. Anyway, so let me show you data for many years. So this is data actually from really long range. It's what it is 32 years, right? Something like this. So more than 30 years of data. Okay. And so we, just for purpose of visualization, we separated data from in this range and this range, but this is basically kind of the same thing. Anyway, so this is different symbols for different years. And on this graph, income is normalized to average income. Okay, so what we see is the following. First of all, on the inset, this is inset. Okay, this is in log linear scale. Income is linear, normalized in this. So this is 1 unit of temperature, 2, 3, 4 unit of temperature. So in other words, average income twice, 3 times, 4 times average income. And you see data basically fall in a straight line. So the lower part of distribution, it remains exponential. Okay, it's here and here as well. Okay, in log, this is the main panel is in log scale. So this exponential graph becomes this. Okay, and data points basically collapse on the same curve. So what we observe is the lower part of the distribution, if you properly rescale it, it simply does not change. So 30 years pass by, but relative inequality within lower class simply does not change at all. It remains exponential. It's given by exponential function. Okay, scale changes, but the relative inequality does not change. And my interpretation is because this majority of population is like thermal ensemble. It's like thermal bath. Okay, it is in a state of maximal entropy, and it's in a thermal state. So that's why it is so stable in equilibrium. Okay. However, on the other hand, in contrast, the upper part of the distribution, that we have this power law, it does change significantly. In fact, it increased significantly during this period of time, and perhaps actually less so in this period of time, more recently. So bottom line is the power law part does change, significantly. And also, what we also notice that it sort of expands the boundary between lower class and upper class. It sort of shifts toward lower income. So in other words, now, as opposed to in the past, the power law starts from a lower income than it used to be. So in other words, this kind of shrinks a little bit, and this kind of expands a little bit. Okay, the power law, but still it covers only a small fraction of population. So basically, the conclusion here is that this two-class structure is extremely stable for more than 30 years of data. And that's basically empirical finding that was not known. I mean, power law was known to the economists, but the fact that there are exponential and power law, that was not known. So that was our empirical discovery. Okay, so once we make this two kind of class decomposition, that's basically the fit to the whole distribution, but two simplest mathematical functions, then we can extract parameters of the fit, right? So it is characterized by a very small number of parameters now, even though there are many data points. But you can reduce those data points to a small number of parameters. The parameters are temperature for the exponential part, the average income. It is the slope, the Pareto exponent for the upper part. And it is basically the crossover point where we have transition between these two. And that's basically three parameters. The whole distribution reduces to three parameters. And we can extract, measure those parameters for all those years. And now I can show you next slide, the time evolution, historical evolution of those parameters. Oh, I'll skip this. I'll skip Lorentz curve. Okay, this is time evolution of the parameters. So this is a little bit busy plot, but let me go kind of slowly over this graph. So let me go with the top panel. On the top panel, this is on the horizontal axis, there is time. This starts about 1983 to about 2015, I think, in this case. And actually, we have more recent paper with even more recent data, but I didn't have time to include. But anyway, it's pretty much the same. So what we see is the following. So there are several graphs. So this is the temperature. So temperature, remember, is the average income of the lower part of the population. So on average, it increases on average because of inflation, but it has some very uneven parts. It grows here, then flat here, grows and flat here, grows and flat here, right? And so what are the regions? So this is the time of boom, the bubble, and this is time of recession, depression, whatever. And this is boom, and this is recession, this is boom. And by the way, right now, in case you follow the news, right now, it seems like the United States and perhaps much of the world economy enter into some recession. So recession is just starting. Economic recession is just starting right now, after the previous bubble that was before. Okay. So anyway, this is temperature. That is the average income of the majority, the lower class, and this is the average income of the whole ensemble of all population, including lower and upper class. And you see the curve has some spikes. Okay. And what are those spikes? Actually, now, what is really, what I think what illustrative parameter is what I call F, the fraction of income that goes to the upper tail. Remember that the number of people in the upper tail is relatively small, few percent, but they account for significant fraction of total income because they have very high income, right? And this fraction of income that goes to the upper class can be easily calculated in the following way. You can take the average income of the whole ensemble, all population, and take difference of this with temperature, which is average income of the lower class. You see, in other words, the difference between average income of the lower class and average income of the whole system, and the difference actually what goes to the upper class, and then we normalize the average income. So that's actually, and so this is shown by this red curve. So the red curve and the scale is here. The scale is on the left side. Okay, so that is the fraction of income that goes to the upper class. And what you see is the following. In the early ages, the fraction of income going to the upper class was really small. It was of the scale of, a few percent. It was like few percent. Then it has been increasing, okay, but relatively steadily. For the next, during the 80s and 90s, it had been steadily increasing. But then, very importantly, there was a rapid increase during this time from 95 to 2000. What was that? That was, if you remember, I'm not sure, you're younger than me, but I came to the United States around this time. That's when I came to the United States. I became assistant professor and postdoc assistant professor, right? So what am I remember that? That was dot-com bubble. That's where internet started and etc. So it was a bubble in the stock market. Stock market was going up, and so the income of the upper class was increasing very rapidly. Notice upper class income was increasing much faster than income of the lower class of the population. That was a bubble, a financial bubble. Okay, and then the bubble crashed. That was dot-com bubble crashed around the year 2000. So the income of the upper class shrunk because stock market crashed, and we get recession. So income of the lower class was flat. But then next bubble started, housing bubble, this subprime mortgages and all that stuff. So that was housing bubble as opposed to stock market bubble. And again, income of the upper class increased, very significant. It exceeded 20%. You see, at that peak, it was reached about 20% of all income was going to the upper class. But that was a bubble, and bubble crash. That was a big crash of year 2008. Okay, and then income of the lower class was flat because it was recession. And then next bubble started. And what is next bubble? I think that next bubble is like, bailout. It was started actually by government, by central banks, because central banks said, oh, we have a big financial crash, so we need to recover from it. We need to save the economy. And central banks, like American Federal Reserve, started to print money and pump, huge amount of money into the system. And that caused another bubble. I call it QE stands for quantitative easing. That is a technical term, obscure technical term Federal Reserve uses for printing money and throwing it into the economy. That's next bubble started and was continuing, I would say, until recently. Of course, it was COVID. This is outside of the, of my data, but just jump into the present moment, which is 15. We are now around here somewhere. There was a COVID. COVID was big disruption. Central bank printed even more money because of COVID. But now we are entering some kind of recession. Basically, we're entering at a crash of that last bubble that we had recently. So anyway, as you can see, just looking at the income distribution, when I say crashes, usually people like stock market goes up, stock market goes down. But what I look here at, I look actually at inequality of the whole system. So essentially what we see is that income inequality peaks, during speculative bubbles in financial markets. And this graph is so-called Gini coefficient. That's another measure of inequality. This was defined on the previous slide, which I skipped. But anyway, that's what economists use to measure inequality. And then the basically has very similar shape. It has peaks and dips, peaks and dips, peaks and dips. So in fact, we derived a formula that relates Gini coefficient, as the economists like, to this fraction of income that goes to the upper class. And there is one-to-one correspondence. One simply defines the other, okay? Okay, now I'm actually approaching 1 hour of my talk. I will talk a little bit more and then I stop. Just a few more things I will ask for questions, invite questions. You might start thinking about questions because I will invite questions pretty soon. You might start thinking about it. So a couple more things. One thing is Pareto exponent. So this graph is exponent alpha, power law. Remember, power law has a parameter, which is the exponent. And this exponent has been, it has value about 2, but it has been decreasing towards 1.5 in this, in this time period. And notice what, when I was giving these talks for 20 years, and if I was giving talks like, way back, I would say if I extrapolate this curve at some year around now, if I do just extrapolation, this exponent would reach value 1. And when it reaches value 1, that means the first moment of the upper tail diverges, becomes like the integral becomes infinite, it diverges. If exponent of power law reaches 1, the integral becomes unnormalizable. That means that the upper class would take out all money, the share of upper class would go to 1, to 100%. Okay, so everything will go to upper class, nothing will be left for the lower class. So this is like a singular point, this is like a singularity point. And you see, if you look at this preliminary data, it would have extrapolated to this singularity by now. But it did not happen. Actually, what happened around year 2000 is it's saturated. So in fact, the whole distribution looks like this. The exponent decreases, has been decreasing. That means the tail is getting fatter, but then it's stabilized. And actually, for the last 20 years, it's actually more or less constant. It's called bumpy plateau. It goes up and down, up and down. But on average, it's kind of stabilized at actually at a value 1.5. Okay, this is, if you look here, is actually 1.5. Okay, so that's one observation. So in fact, that means the growth of inequality has actually stabilized in some way. Another interesting observation is that a fraction of population in the tail. Again, what is percentage of population is in the power of the tail? It used to be very small, like 1%. But then it has been actually increasing. And now it is about 5% or so. So actually a bigger proportion of population belongs now to the upper class than it used to be. So the upper class in some sense is expanding as a fraction of population. Maybe it is stabilizing, who knows, but it has expanded. But it's still a very small fraction, but it has expanded compared to what it used to be. So there was significant, I would say, qualitative change of the economy from the 80s to like 2000, because the upper class has increased significantly. That tells us something, what exactly we need to think about, but it tells us something. Okay, so now I've spent 1 hour about, okay, so I'd like to make I'd like to invite questions from the audience. Okay, I have other stuff to present, but anybody has any questions?
Yes, I think there is a question in the Zoom chat.
Okay.
It says, what do you think that econophysics could do different compared to other classic approach in economics? In other words, what could be the transcendence of econophysics in our understanding of everyday economics topic?
Okay, yes. Okay, that's a very good question, very relevant question, right? So yes, of course there is economics, the big subject of economics. And what is that econophysics that brings new and different, etc. And I would say this is like, in some sense, the question, I mean, the answer to this, in some sense, work in progress, meaning, as often happens in science, right? We try to, uncover something, and sometimes we succeed, some not, occasionally we succeed. It's not very often that we discover new things or make some progress. It's not like every paper discovers something new. I would say most papers actually repeat the same thing that was done before, but occasionally there are breakthroughs. Occasionally there are some new things that move us forward. And I would say the following: that I can list several items. I think the most important point is this: that physics gives a different perspective on these economic questions. There are various economic questions, like for example inequality. What is the origin of inequality? What is the nature? Whether something can be done about it, or whether something should be done about it. That's all open questions. And physics gives a different perspective from economics and social sciences more generally. So you see, one message is that, as I pointed out, that from a physics perspective, from statistical physics perspective, this inequality, at least most part of it, the exponential part of it, is really a consequence of basically entropy. It's a basic applied theory of probabilities. You basically apply theory of probabilities to the big ensemble, and you find these results. And theory of probabilities tells you that you should expect exponential distribution. And in fact, it is exponential, right? And economists had no idea about this. They had no idea about shape of the distribution, etc. So if nothing else, we managed to find empirically, it's very simple empirical law that describe the structure of inequality. And once you know this very simple empirical law, then basically you reduce all this data to a small number of parameters, and then you can study how these parameters change in time and evolve in time, and maybe change between different countries, etc. So let me just make some analogy of this, maybe a little bit immodest, but you see how it worked in about Kepler's law. This is a little bit far away analogy, but it's kind of important. In the Middle Ages, or like late middle, after Middle Ages, okay, there were astronomers, right? And what the astronomers did? Astronomers collected data, right? They put the telescopes, well, after the telescope was invented, of course. They put telescope and they recorded positions of, objects. So for example, planets, right? They just recorded positions of planets as function of time. And they had huge arrays of empirical data. I mean, they just had tables of tables and tables of recorded positions of, say, planets, okay? So this is empirical, hard empirical data, pure empirical, and it's a very long list of numbers, positions of the planets. This is empirical science. This is a data collection, but there is not much. It's very important, but there's not much insight. And there is economic data as well, like income data. There's lots of numbers, column tables and tables numbers. Okay, but then there was one astronomer, Tycho Brahe. I think it was in Denmark. I think Scandinavia. And he had a postdoc. His name was Kepler. Kepler was a postdoc of Tycho Brahe. He was a young assistant. And Kepler looked at these tables of data, columns of numbers, and then he had some idea that, well, I don't know how he got this idea, but he got this idea that he made a hypothesis, a conjecture, that if maybe planets move on ellipses. He made this conjecture, they move on ellipses. So in fact, these trajectories are really simple, described by elliptic function. And they tried to fit the data, and he found, very good of the data. He found really great fit of the data. And he found suddenly that all these, thousands of data points can be reduced to a few parameters of the ellipse. Ellipse has, a-axis and b-axis and ellipticity and all that. Ellipse is parameterized by like a small number of parameters. And so he realized that all this data can be reduced to a small number of parameters for ellipses. And this is what I call compression of information. Now, instead of thousands of data points, you only need 2 or 3 or so parameters for ellipse, and then you know everything about the planet. This is huge, I would say, breakthrough in terms of like data science. This is, realizing there are empirical regularities in data is actually a big step toward discovery. And to some degree, that's what we found, that the thousands of data points for, say, income distribution. This is only for United States, but if I have time, I'll show you for other countries. Now this is done for all countries around the world, including Mexico, by the way. I received an email just before my talk, a couple of days before my talk, an email from a student who is actually at Rice University, but he attended my colloquium at Rice several years ago, same talk. And then he looked at the Mexican income and wealth distribution in Mexico, which again is publicly available data, made this kind of graphs and found exactly the same structure, exponential and power law. He sent me an email just a couple of days ago. I didn't have time to include it. So this actually works for many countries. Okay, but then we're talking about Kepler. Kepler did empirical progress, okay, but still, why ellipses? No idea. Ellipses work by why? And then came Newton. And Newton, well, also had some insight, who knows how, that if, Newton invented, Newtonian dynamics and law of gravity, and Newton have shown that elliptical orbits, in fact, are consequences from the law of gravity and, well, Newton's equations of motion. So Newton basically derived elliptic motion from his fundamental laws. So you see, the progress of science was going in 3 steps, right? Empirical collection of data, then finding some empirical regularities, analytical empirical regularities in the data, and finally some sort of analytical theory to, explain or, produce those empirical laws. So I think what I have been doing in this econophysics, I'm somewhere on this Kepler stage, that I found some very, very well-known quantitative regularity in the data, but I'm not sure we are at the Newton stage. I'm not exactly, maybe again, if I have time, I will show you something. How to derive? You may ask, how can I derive now? If you agree that distribution is exponential in power law, can I now derive it from some equations? Can I get some insight where it is derived from? I will show you something maybe on the next slide. So this is different side philosophy. It's not a philosophy followed by the economists. All this philosophy kind of orthogonal to the way of thinking how economists and social scientists are trained. They're trained totally differently. This is just orthogonal space for them. But this is how physicists think about things. So that's maybe my best answer to this. There are other items where econophysics made some progress, but maybe I'll kind of focus on that part for now. Okay. So anyway, my time is running out. So maybe let me now move maybe more quickly to the rest of the talk. Okay. So I showed you data for United States. What about other countries? Now, very quickly for other countries, few samples. This is data for United Kingdom. So this is paper we did actually with Chinese researchers. So we actually look at the data from 67 countries around the world. Okay, first we look at, just to give an example for the UK. So, United Kingdom. So United States is not special in this regard. So we'll download the data from the, British, data source from their British tax agency. Okay, and this is, again, CDF means cumulative distribution function. And so this is, again, as a function of normalized income, income normalized to temperature in logarithmic scale, so it's log linear scale. And you see the lower part of the distribution follows a straight line, which means it is exponential. The upper part deviates because of the power law, okay, but it's difficult to get power law because data is limited at high end. It's a survey of, yeah. So if you remove just a few points at the top, because this is power law, this is upper class, so we remove them. Okay, and this is called truncated CDF. You see, this is a perfect, perfect exponential distribution for the lower part of the population. There are basically no data at the low end, and the reason is because by the British laws, people who have low enough income below some threshold, they do not need to pay taxes. They're exempt from taxes, and they don't have to report the income for taxes. So there is actually no data at the very low income. But where there is data, it follows exponential law for many different years. So UK is basically the same qualitatively as United States. Okay, and this is data actually now, this is a very busy slide. This is for 67 countries in the world. This is European Union countries. This is other region of the world. Let me see if I have Mexico here. Let's see, yeah, Mexico here, Mexico, okay. So you see, this is income distribution in Mexico, okay. This again, normalized income in log linear scale. And again, this is the lower part of the distribution is exponential. So the way, basically the conclusion here is the middle part, This is, by the way, this is China, just for other countries, China. In the case of China, this it is for a particular year, for one, I don't, what was a year? I forget, but it's for one particular year, recent year. Okay, so in case of China, it extends pretty far away, up to 5 times the average income. In some other countries, power law starts, etc. So here we have it only up to maybe 3 times the average income. The availability of data varies between different countries, but it's a very, very common. Okay, so I think I more or less exhausted the empirical part of the talk, right? Now, in the next maybe few minutes, let me maybe show you some few more slides about kind of a theory. Okay, so okay, empirically we hopefully agree that there is exponential part for lower and a power law for upper, but can we derive it from something? Okay, let me now try to do a little bit of mathematical theory, and this is about the origin of 2 classes. Why we have 2 classes? Okay. And from my perspective, is because they have different sources of income. So it is salaries and wages for the lower class, and it's capital gains and investments for the upper class. So upper class derives income from and wealth from investments, whereas lower class people, they simply receive salaries. And these are different type of economic processes. That's where economics, comes into play. Yeah. And one can, yeah, I'm not, and I will model them mathematically in this next slide as additive process for lower class and multiplicative process for the upper class. I will explain in more detail in the next slide. And then that will give me different dynamics. From social perspective, if you like, you might think that this is different between employees and employers, as people like Karl Marx told us. Maybe I should mention that my undergraduate education was in the 1980s at the Soviet Union. Okay, and we had mandatory courses of social science, a mandatory course of political economy. So my economic education is political economy, and The Capital by Karl Marx was mandatory reading. Okay, so to some degree it also motivated my look into this. And surely enough, I heard about 2 classes from my undergraduate education. It was actually quite interesting, interesting that many years later, as I see that empirical evidence for these 2 classes. So anyway, so the class theory of society has a long history. It's not recent, right? But what we added is this data kind of aspect on it. And also, I remember in my very simple computer simulation, I only get exponential distribution, right? The simulation I showed you earlier. I do not have any power law. So to get power law, we need to make model more sophisticated. And this was actually done by some people. Ian Wright, who's a computer scientist. So he did a more sophisticated model where some agents become entrepreneurs become employers. So some agents establish company, then hire other agents. So he devised a more sophisticated computer model where there is spontaneous emergence of two classes. Okay, again, some people become entrepreneurs, employers, and some agents become employees. And then, of course, nature makes difference. So anyway, but I won't go into this, it's complicated. Maybe I'll skip. This is data for Sweden, maybe I'll skip it. Yeah, okay, because time is short. I just want to show a Fokker-Planck equation. So how you can model this mathematical description of two classes. And then yet another approach, you choose Fokker-Planck equation, which is very well known in kinetic theory. Again, in non-equilibrium statistical physics, it's basically diffusion equation. It's basically diffusion equation. And so, but it's very, very general, and it's diffusion in any kind of space. It can be diffusion in real space or some other space. So here we apply it to discuss diffusion in income space. So what we want to know, what we want to calculate is probability distribution of income, so use letter R for income, okay, as a function of time t. So that will be probability distribution of income R as a function of time t. Now income obviously is positive, okay? And then let's assume that the income changes by small amounts after some time t. So in other words, your salary maybe increase a little bit next year, maybe next year, may even go down. We had furloughs. Our salary was occasionally decreased because of financial crisis. So if income changes is sufficiently, if this variable R changes by small amounts over time t, then we can write some sort of partial differential equation. This is in many physics textbooks, such that the time derivative of this probability distribution is given by this right-hand side. It has first term which has first gradient and second term which has second gradient, second derivative. Okay, so basically this has two coefficients, coefficient A and coefficient B. So A is called drift, and the second is called diffusion. Okay, so this drift and diffusion are the two coefficients. So what is A? A is average change of income per unit time. So this is like average change of income, okay? And that if you only have that, you'll have just drift of the whole distribution function. But then there is second coefficient. This is second moment of income change per unit time. This is called diffusion. And diffusion doesn't care whether income changes up or down because it's squared, right? Whereas the drift does care. It can be positive or negative. So anyway, so this is diffusion coefficient basically, and this is drift, where a system just flows somewhere. So this is a very simple, it's equation used in all kinds of things, including stock market and any kind of stochastic processes. But now let's look for stationary distribution. If you want stationary distribution, stationary solution, we set time derivative to 0, and then it follows that this thing, which is called the probability flux, must be equal to 0. So in stationary case, we get this equation, which is now ordinary differential equation. And then we can try to solve this equation. But then to solve it, we need to make some assumptions about coefficients A and B. Okay, and now that's very important. Now I make the following conjecture, that for the lower class, the change of income is independent of income itself. That's called additive diffusion. So for example, my salary has some value, but maybe next year, maybe it increased by $5,000. It will increase by a certain fixed amount, not in proportion to my income, okay? So in this case, delta R is independent of R. So then the coefficients A and B, some sort of constants, they are not functions of R. And if these are constants, you easily solve equation and you get exponential distribution. And the temperature is the ratio of coefficient B and A. This is known as Einstein relation between income and diffusion and mobility. So if you have additive diffusion, then we have exponential distribution as a stationary solution. But you may also consider something else, multiplicative diffusion, where income changes are in proportion. So my income may go up maybe 2% or 3%. So if it is in percentage, then it is in proportion to income, and that's different type of dynamics called multiplicative dynamics. And then coefficients A and B are proportional to R and R squared. You plug them into this equation, very easy to solve it, and you find the power law. So multiplicative diffusion leads to power law, okay? So from my perspective, then lower class described by additive diffusion and upper class by multiplicative diffusion, different mathematical processes, but most interesting if you come combination of both, okay? So if you may have coexistence of these two processes, so you have both additive and multiplicative, the coefficient then the sum of two contributions, right? And then you solve this equation. Solution looks kind of complicated, arctangent, kind of complicated function. But in fact, this function has actually a simple limit. It simply interpolates, this function interpolates between exponential function at the low end and characterized by temperature, and power law function at the upper end and characterized by this exponent. And then there's another parameter which is crossover between these two parts. So this function actually is a certain function that interpolates between exponential at the low end and power law. So it's a smooth interpolation between two fits. And this function fits, the data, IRS data very well. So the points here are the IRS data, and this is the fits to this function. So in other words, we can we can derive from this stochastic process with additive and multiplicative components, we can derive actually a smooth function which interpolates between these two limits, and it agrees with data very well. Oops. Yeah, so let's see. So what we did is, okay, so we published this in the reviews of, this is another contribution. We published this in Reviews of Modern Physics and New Journal of Physics. And this is another paper speaking about economists, etc. So Matteo Marsili, he's an Italian physicist who works in Trieste, International Center for Theoretical Physics in Trieste. And Davide Fiaschi, he's an Italian economist in Bologna. So this paper is a collaboration between an Italian physicist and economist. And then, well, because it was physicists there, they actually derived the same result independently. But it took them much longer to publish. It took them three years longer to publish this result. Okay, because they published this in an economics journal. It takes forever to publish an economics journal. But anyway, then what I learned at the conference, that in fact, this formula was actually derived for the first time in the late 19th century by Carl Pearson, which is a very well-known statistician. Okay, it was late 19th century when he derived that formula also, in a different paper. The paper was published in, Proceedings of Royal Society. But, the title of his paper was On Mathematical Theory of Darwinian Evolution. So he tried to apply theory of probabilities to, to biology. That was his motivation. And the paper is very long, it's very difficult to read. It's not a very, they're not very well written, let's put it this way. But then he gets this formula. So in fact, this formula is known as Pearson type 4 distribution since late 19th century. So anyway, at this point, I think I exhausted pretty much all of my time. This last part of the talk of which I don't have time, so maybe I'll jump to conclusions, and I stop for questions. And so you will, let's see how I do this. Okay, so now I'm at my conclusion slide. Okay, so this is my conclusions. I will probably not read them because there are many, I said most of them. I want to just point out that all the papers are available on my website, so if you want to read, and also recording of my talk, etc. And also there are some books. There's a nice book, popular book written by science journalist Nathaniel Grunewald. He's a science journalist, so he wrote a popular book. And one of the chapters covers, what I told you, that kind of theory. It covers other chapters which are also very interesting. So anyway, this is some readings I recommend. Anyway, let me stop now and take some questions, and thanks for your attention.
Hello, can you hear me?
Yes.
Oh, yeah, I have a funny question. If that's okay.
Yes, go ahead.
So how does one join the tail if you're not in the tail?
Okay, I see. Very good point. Very good point. How one can personally get into the tail, right? Okay, how to, like career advice, how to get into the tail. Okay, so let me tell you my speculation about this. This is my speculation. Let me jump to some slide. Let me go to slide. Let me go to some slide. Maybe this one. Okay, so let me go to this slide. So the question is the following. Most of us, I'm pretty sure, pretty much everybody in this room, we are certainly myself for sure, we all pretty much belong to the lower class. If you look at your income, by the way, what is the boundary, say in American dollars? The boundary is around here, and this is in 2015, but it didn't change much. This is roughly the boundary. And boundary, this is actually $200,000 annual income. because you see this is 100 and this is 200 on logarithmic scale. So the boundary is roughly speaking 200K in the United States. So if your income is below 200K, you're in the lower class. That's my case for sure. But if you're about 200 or sufficiently about 200, you're in the upper class, roughly speaking. So how to get there? And here's my speculation. My speculation is the following. Well, of course, so here's it's my take on it. Well, first of all, let me tell you this. I showed you the simulation right at the beginning. And this simulation produced exponential distribution, right? But it did not produce power law, right? So you might ask, what kind of ingredients I would need to add to my simulation to produce power law, etc. And if you think about it from conservation perspective, sort of conservation of money, let's say these people have, very high income, right? And the question is, people in the tail, where does money come from, right? The money must be coming from somewhere. Obviously, they're coming from the lower class, from whom else it can possibly come, right? And why it is few people here collect money from so many people there? I would say that means we have a different network topology. So it reflects network topology. Network topology is very important because in my original simulation, my network topology was extremely primitive. Remember, in my original simulation, everybody can make transactions with everybody, right? So that means there was no structure whatsoever, and everybody was in the same position. That's why we get exponential. But the real society, network topology is very different. Okay, so for example, the trend that we have in the recent years, tens of years, is the following: we have very high concentration. For example, especially in computers, in IT technology, etc. For example, I am given this talk. All of my computers are Apple computers. I have Mac desktop, I have iPad, I have Apple Pen, etc. I have iPhone. I live completely in Apple ecosystem. That means what? And there are millions of people like that, okay, who basically buy products from Apple, right, and give money to Apple, right? So this Apple is like central node in this network, one of the central nodes in this network, which is connected to huge number of customers. And this company, collects money from huge number of people, right? So it's a hugely central node. Because it is central node and collects money from huge number of people, obviously the head, like CEO of the company, well, naturally, because there's a huge flow of money, CEO can take some small fraction of it, will be a huge amount and has huge money. Another player is Microsoft, right? Another half of the world population uses, Microsoft computers, and they also in a huge node, another half of population, okay? And there are a very small number of other operating systems. There are only a few operating systems in the world, right? It's not like, there are no hundreds of them. There are maybe like single digits of operating system. And that goes everywhere. For example, coffee, I go to Starbucks every day to have coffee, right? Anywhere in the world I go to, well, Starbucks. And millions of people order it from Starbucks. It's a hugely connected node. And by the way, why it is so? Because I can make orders on my iPhone, right? So because of digital technology, in other words, what I'm getting to is the digital technology allows huge scale up of a business. Okay, so in the very old days, like every town, every city, whatever, they had their own coffee shops. This coffee shop. Okay, or say taxi company. When I was arriving to I was traveling somewhere in the old days. I come to this town and I need to find out phone number of a local taxi company to take me to my hotel. I had to know phone numbers for different taxi company for every city, right? Not anymore, right? All I need is Uber, right? I go have Uber anywhere in the world. I call Uber and Uber comes, right? So digital technology allows huge concentration, huge centralization. So these central nodes like Uber, Starbucks, Apple, you name it, they become hugely connected. Okay, and this is enabled, and I think the underlying reason is digital technology because you can scale up business digitally much easier than physically. In the old days, we needed it was difficult to scale up business. It was more difficult to scale up businesses. Now with digital, if you have right idea and if it catches up, etc. If certain conditions come together, it may be scale up in a huge way, like Google did, and all this Google is one example, etc. from a recent startup. So that's roughly speaking, I think, what's going on. Of course, there is a huge number of startups. And only a very small number of them will succeed and grow into super places, okay? But those those who will grow into super places, they will be, you know, well, basically like super rich. So bottom line, if you try to get there, well, maybe if you come up with a great digital idea, you may get there, and then you have millions of customers, and then will collect a lot of money from, even if you charge them very little. But with huge number of companies, you collect a lot. But your chances of getting there is, you know, there are millions of people who are trying to do the same. Okay, yeah. So that's roughly speaking my answer. Okay, any other questions?
Oh, I think the time has run out. We are now
I have
expecting
one
the-
question. I have one small question.
Okay.
Considering the information available today, which economic indicators do you consider the most relevant?
It's actually a very complicated question, in the sense that, you see, it depends what you're looking for. I mean, it depends on the definition most relevant. You know, most relevant for what? Depending on what is relevant. You know, these are different indicators. So I personally think that, in my opinion, this parameter, the fraction of income, I mean, this is parameter which I introduced, and I think it's a very important parameter. I mean, if given two-class decomposition, the share of income, fraction of income going to the upper class is important parameter. It was not known before. But whether this is the most important depends on the kind of purposes that of your interest. That's my short answer. It is of interest to me and many other people, but is it of interest to everybody? I'm not exactly sure. Okay, I think I ran out of my time. Probably next talk, you know, need to start, right?
Yeah, thank you very much, Dr. Yakovenko, for your lecture in this International Symposium on Physics. We would
Okay,
okay. We would also like to take this opportunity to thank our sponsors, without whom this event would not be possible: Ternium, Climate AI, and HV. Thank you very much for your presence, and see you in a few moments for Ana Maria Cheto's lecture, Realistic Approach to Quantum Phenomena, which will start in a few moments here at the Congress Center. Thank you, Doctor.